form of complex numbers. Take one. Take two, actually. Okay? So a complex number, you may know, let's change colors because it's not a good color.
Did you turn the lights off?
Oh, turn off the lights. Well, it'll get brighter in a second. It takes a while. But, see, it's warming up. A complex number is a number of the form a plus bi. So a complex number would be something like 3 minus 2i. Now can you see okay, Annie? Yeah. That's a complex number. So it has, this is called the real part, and this is called the imaginary part, imaginary. And there are pure complex numbers. So a pure complex number is just like 6i or negative 5i or something like that. Those are pure complex numbers because they just have an imaginary part. But complex numbers are written in this form, so you could rewrite this as 0 plus 6i and 0 minus 5i. Real numbers are also complex numbers. So you could have like 6 is a real number, but if you wanted an I part, you would just write that as 6 plus 0i, right? It has an imaginary part, but the imaginary part is 0, okay? So all numbers basically are complex numbers, but we don't usually write real numbers as a complex number, but for the most part, we're going to be talking about these kind of complex numbers like this one and this one. And you guys remember what I is? What is I? That's equal to the square root of -1. And even though, you say, well, that's dumb, there's no such thing as a square root of -1. But there are like applications of this in lots of math and in science. And I heard a story about, on the radio about they use complex numbers to model like aerodynamics of cars and stuff. So like when they're modeling flows, there's probably more applications than that, but flows of liquids or flows of fluids and stuff, they use complex numbers apparently a lot to do that. Okay, and I'm sure there's tons more applications. Okay, so then we have this thing that's going to be confusing to you called the complex plane. Okay. And the complex plane looks like this and this. It looks just like the xy plane, except over here this is the real axis, okay? And this is the imaginary axis. And so if I want to plot a point in the complex plane, for instance, this one over here, 3 minus 2i, this is like the I-axis up here, and this is like the real part. So I would go over 3, 1, 2, 3, and then I go down 2. Okay? So this is the point 3, comma, whoops, not comma, 3 minus 2i down here in the imaginary plane. 3 minus 2i would be right there. How would I graph 6? I just go over 6. 1, 2, 3, 4, 5, 6. So 6 is just where it would be. How would I graph 5i?
Up 5.
I just go straight up 5. 1, 2, 3, 4, 5, because it's over 0, up 5. So there's 5i right there. So that's how you graph things in the complex plane. And I know that's confusing because we just talked about this being the I, when we talk about vectors, right? We talk about this being the I-axis and this being the J-axis. So when we're talking about complex numbers, it's kind of like the same thing. This is the X part, this is the Y part, except they're not really vectors, they're just points in a plane. But they work very, very similarly to vectors, okay? So the absolute value of a complex number, absolute value of a complex number if I call that complex number z, if z equals a plus bi, then the absolute value of z, you know this means absolute value, right? Absolute value of z, which is equal to the absolute value of a plus bi. All you do to do that, you do almost the exact same thing that we've been doing by finding the magnitude of a vector. It's just the square root of a squared plus b squared. Okay? And that's
bi squared?
not just b squared, not bi squared, just the coefficient of the I term. Okay? So if they say z, if z equals 3 minus 2i, and then the absolute value of z, whoops, I don't need 2 bars, it's just 1 bar, okay? The absolute value of z is just the square root of 3 squared plus negative 2 squared, which is equal to the square root of 13, okay? Questions about that? Okay? And so, for instance, this point right here, 3 minus 2i, which is right here, this, it's not a vector, it's just a straight connection going from here to here, okay? This thing, what? Yeah, it's like a magnitude of 13. And they call this R, and another name for that, R is equal to the magnitude of the vector z, which is equal, and it's called the modulus, okay? M-U-D-U, but it's just like the magnitude of a vector, okay? So this thing is R, it's the absolute value of the vector, it's called the modulus, okay? So you need to know that. Questions about that, Drew? No. Wow, that's colorful. Okay, moving on. If you want me to go back, tell me. Trig form of a complex number. Trig form of complex numbers. It's just like trig form, very similar, of complex numbers. It's very similar to trig form of vectors, okay? So if you have some, here's your complex plane, mini complex plane, and this is like your I-axis, and this is like your real axis, and you were to draw a point going over this way. So here's some point over here, A plus BI, okay? This is theta, okay? And theta has a name, okay? And I don't know why they have to name it a different thing when it's a complex number, but this here is called the argument, okay? So it's the same thing as the what's the angle called when you're talking about a vector? The angle, I forgot, but this is the theta is called the argument when you're talking about a vector in trig form. And what that looks like in trig form is R, if this is some vector z, not a vector, a complex number, z, let me erase. If z equals, where'd my thing go? Whoa, come back. If z equals a plus bi, that can be written as r times the cosine of theta plus I sine theta. Okay? And this is just the real component. R times this would give you the real component of your complex number, and I times the sine of whatever the argument is times R would give you the complex component of your complex number. Okay? So, questions on that? So you'll see a problem like this. Write 2 minus 2 root of 3I in trig form. Okay? So, you guys, what are you doing over here? So, can you see that okay? Can you see that okay? Okay. 2 minus 2 root of 3I. So, first thing you're going to do is find R. You know how to find R, Trevor?
Would it be the same thing for cosine?
Yeah, but you gotta find R, which is the magnitude. How would I find the magnitude of that?
Would it be there?
It'd be this.
A squared plus b squared.
Yeah, kind of like that. Plus, it's a plus, it's square root of a squared plus b squared. So this is a, this is b. So it's 2 root of 3 squared, like that. Okay? Which gives you, what's 2 squared? 4. What's 2 root of 3 squared? 12. Do you guys know why that's 12? You know why that's 12, sir? Because you got to square the 2 and you got to square the root of 3, right? Root of 3 squared is 3 and 2 squared is 4 and 4 times 3 is 12. And what's the square root of 4 times 4 plus 12? 4. That's equal to 4. So that's your R. Then you got to figure out what theta is, okay? So theta in this case, oh, I didn't say that. So a plus where tangent of theta, okay, is equal again to b over a. And we call this part b, and we call this part a, okay? So tangent theta is b over a, so you know that the tangent of theta, in this case, is equal to, where am I? Negative 2 root of 3 divided by 2, which is equal to negative root of 3. Anyone remember where tangent is negative root of 3? Yeah, where is tangent equal to negative root of 3? No one knows? Tegan knows.
No, I don't know. I'm just wondering why are you using tan? Where did you get tan from?
Because I'm trying to find this angle, right? And tangent of theta is equal to this over this because this is really you're going up b, right, and over a, right? So if I want to find this angle here, I'm going to use opposite over adjacent, okay? So the tangent of theta is b over, just like I did for finding the angle when I'm doing vectors, same way, except, so tangent of theta, if you did inverse, if you want to use your calculators, which you shouldn't have to, inverse tangent at negative root of 3 is going to give you out negative 60 degrees, okay? Or, which is equal to negative pi over 3 radians, yes? No, okay? So when you take an inverse, there's only going to be one answer, okay? But this is, where is that, where is this point? If I go over 2 down root of 2 over 3, so I'm over here, right? Over 2 down 2 root of 3, I'm going to be down here. But I'm not allowed to call it that because that angle has to be a positive angle. So how can I get to here other than going negative 60? How would I get there? 300, okay? So that's what theta is equal to 300 degrees, okay? Which is equal to 5 pi over 3 radians, yeah? So when I'm going to rewrite this, so write 2 root of 3 and this in trig form, it's going to be z is equal to r, which is 4, times the cosine of 5 pi over 3 plus I sine of 5 pi over 3. Just kind of like we did with the vectors. Now, it's kind of good to put that, you should really put the I in front, because otherwise it might get confusing. You're taking the sine of 5 pi over 3I, you know what I mean? So you want to put the I first rather than after. When you're doing like this, you want to put the I after, but when you're writing it in trig form, you want to put the I first, okay? So it doesn't get confused with doing it. Okay, so without, you should be able to do this without a, without having to do all this. What if I wanted to write z equals negative 3I in trig form? Could I do that? Where am I if I'm at negative 3I? I'm straight down 3. 1, 2, 3, right? What's R in that case? What's the magnitude or the modulus here? What is R? It's just plain old 3, right? What's theta? How far is it from here to here? 270 degrees. So theta is 270 degrees, or 3 pi over 2 radians, right? And so to write this, right? Do you understand what's wrong, Mitch? Why is R 3? Because the length, the distance from here to here is 3. Because that's what the modulus is. It's kind of like the magnitude, right? It's like the magnitude of a vector. So it's just 3. So since it's on the y-axis, I could just count 1, 2, 3. I could say, so 3i is the same as 0 plus negative 3i, right? And so if I want to find r, I could go r is equal to the square root of 0 squared plus negative 3 squared, right? Which is equal to 0 plus 9, which is equal to the square root of 9, which is equal to 3. I could go through all that, or I could just count 1, 2, 3. See, that's easier, isn't it? Just count. So if it's on the x or y axis, the modulus is just, you know, the point on that x, the how far it is from the origin. Get that? The modulus is always positive. Yeah. So z is 3, like Connor said, cosine of 270 plus I sine 270. It doesn't always have to be in radians, but or which is the same as, you could have put in 3 pi over 2 here, and I sine of 3 pi over 2. Same thing. Okay?
And we just leave it that way.
And you just leave it in that form. Yeah, because if I change it back, then it would just change it straight back into negative 3i. See? If I multiplied all that together, it's just going to change it right back into this. For instance, okay, you ready to go backwards now? Did you get confused? No, Cassie didn't get confused. Good. Okay, what if I wanted to write, let's do a new page. Let's change colors. That's what it is. It's different colors. You need a different color. Write z equals square root of 5. I wrote square root of 3, but I meant to say square root of 5. I said square root of 5, but I meant to write. Anyway, this is what I meant to do. Okay. Cosine 5 pi over 6 plus I sine 5 pi over 6 in a plus bi form, okay, which is just called standard complex form or something. Could you do that? What's the cosine of 5 pi over 6? That, very good. Negative root of 3 over 2 plus I, what's the sine of 5 pi over 6?
1/2.
Positive 1/2. And then I could distribute through. So root of 5 times root of negative 3 is negative square root of 15. That's divided by 2. Plus root of 5 over 2 is just root of 5 over 2 pi. And that's how you would write that in complex form, or in A plus B algebra. You understand what I just did? Yes, ma'am.
Wait, can you say one more time how you got from the second step to the last one?
From here to here, I just distributed through the root of 5. Root of 5 times root of 3 is negative root of 15. And root of 5 times 1 is root of 5. And there's a 2 down there, and it just stays. Okay? Isn't this exciting? You don't think this is exciting? Because, you know, with imaginary, if you have imaginary numbers, you could, you know, I don't have any friends, so then you could do this with your imaginary friends. Okay. Saying, I could see why you don't have any friends if you tell them those stupid jokes all the time. Okay. Multiplying and dividing complex numbers. This is why this is kind of nice. Okay. So multiplying and dividing complex numbers. So you have two formulas, okay? If Z1 is equal to R1 times the cosine of theta 1 plus I sine of theta 1, okay? And Z2 is equal to R2 times the cosine of theta 2 plus I sine of theta 2. This is a formula that you're going to have to know, okay? Then Z1 times Z2 is equal to R1 times R2 times the cosine of theta 1 plus theta 2 plus, yes, right, plus I sine of theta 1 plus theta 2. And with division, Z1 divided by Z2 is equal to R1 divided by R2 times, guess what, goes here. What do you think? It's subtraction, okay? Helps to write things down. Helps you remember them, Danny. I know, but like these formulas. So these formulas are good to know. So if Z1 equals, we're going to just, I'll show you what this means, okay? If Z1 equals 8 times cosine 120 plus I sine 120, okay? I sine 120. That's in degrees. And Z2 equals 6 cosine 150 plus I sine 150. What this formula says is that if I have two complex numbers which can be written in trig form like that, then Z1 times Z2, if I multiply those two complex numbers together, I get 8 times 6, that's R1 times R2, is 8 times 6, times the cosine, and then I add the two angles together. So cosine at 270 plus I sine 270. You guys see what I just did? I added together the angles and I multiplied together the moduli. Is that the plural of moduluses? Moduluses? Okay. So Z1, that's equal to 48. What's the cosine of 270? It's cosine of 270 is 0. Plus I sine of 270, what's the sine of 270? Negative 1. So negative 1I, so we could just call it negative I. So that's equal to negative 48I. What does that mean? So it means that if I have two complex numbers, okay? One that, so this one you could write in a plus bi form as 8 times, what's that root? Where would that be? It would be somewhere over here, right? So here's this one, and here's this one. 6 cosine 150 would be like over here. So if I multiply these two complex numbers together, I end up getting this complex number, negative 48i, over here. And so it's kind of like trigonometrically, it comes from here, but algebraically, this is what you would get as your get this answer that is negative 48i, which would be way down here somewhere. Okay? And I guess you have to do that in like engineering applications and stuff, like multiplying together complex numbers. Like maybe you had a complex number like 3 minus 2i, and you want to multiply that by 5 plus 6i or something like that. So you can find the angles that they make, and then add the angles together and find their moduli and multiply those together, and you would find the new complex number, which seems like a complicated thing, but if you're doing something like this, 3 minus 3i, and you want to raise that to the 5th power, I just want to show you why this is kind of cool. Okay? Well, I'm not going to show you that yet, because that's called the Mott's theorem, which we'll talk about tomorrow. But this stuff is very helpful for doing stuff like this. You wouldn't want to multiply 3 minus 3i times 3 minus 3i times 3 minus 3i 5 times, because that would get really complicated, you know. But you can add up their angle 5 times and take the modulus times itself 5 times, and you would have a new complex number. We'll talk about that more tomorrow. Just z1 divided by z2, real quick, this is the last thing, is this divided by this. So it's just 8 divided by 6 times the cosine of, you subtract the angles, okay? 120 minus 270. What's 120 minus 270? 120 minus 150. What's that? Negative 30, okay? Plus I sine of negative 30, okay? Which that's in degrees. And you can simplify that to that's equal to 4 over 3. Cosine of negative 30 degrees, I believe, is positive square root of 3 over 2. And the sine of negative 30 is negative 1/2. So if I multiplied that out together, I get this 2 cancels at that. I get 2 root of 3 over 3 minus 4 times 4 over 6, which is minus 2 over 3 in the I direction. Okay? So I just simplified those fractions. Do you see what I did? Anyone? Yeah? Okay? So I could take these two. So if I want to divide this complex number by this complex number, it just comes out to be this, because I subtract the angles, I divide the r's, and I end up getting this, and that's all she wrote. Okay? Done? That's part 1. Part 1. But we're done for now, for today. Okay. Thank you. Yeah. You're done talking already? I was hoping there was more.